Okay, up on the board you can see we have molecular geometry, which is going to help us and tell us the shapes of molecules. You're probably going to need to take out your AX packet also, because we're going to go back and forth and use that AX packet. So get that out and have that handy so we can reference that. All right. The molecular geometry, our learning target is to determine which type of model is the best representation for a variety of compounds. And how are we going to do that? Well, we are going to state the valence shell electron pair repulsion theory. We're going to identify the AX method of molecular geometry. We are going to determine the molecular geometry of a compound. And finally, we're going to represent compounds in a perspective drawing, which we're going to end up calling Fisher projections. Okay? Fisher projections. So, determining the shape of a molecule. If we look at this Lewis structure, okay, the Lewis dot structure here, it shows us a two-dimensional view. Okay, it shows us a two-dimensional view. However, when molecules are bonded together, they are three-dimensional. So what looks like this looks like 90 degrees. As I look at my bonding angles, it looks like 90 degrees right here. Okay? Looks like 90 degrees up here. All of them look like they're 90 degrees. Okay? However, this shape is what we actually call tetrahedral. When we take the tetrahedral shape, you can look and see that the actual bonding angles between the different molecules here, or the different atoms, the bonding angle is 109.5 degrees. So it is more than that 90-degree angle. So how do we find the shapes of molecule? We use the VSEPR theory, the valence shell electron pair repulsion theory. And what that theory states is that molecules will adopt a shape that is lowest in energy by minimizing the valence shell electron pair repulsion between adjacent atoms. Now, what that long definition there means is that electrons are negative charges. The negative charges repel each other, okay? Whether it's a shared bond or a lone pair or an unshared pair. We call the unshared pair lone pair of electrons. So there is a repulsion between these electrons, and that repulsion is what determines the shape of the molecule. So, basically, in layman's terms, atoms in a molecule try to spread out as far away from each other as possible because the negative charges are repelling each other. I look here at methane. Like I said before, that appears right there to be a 90-degree angle. Okay? However, these angles are not on a two-dimensional plane. They're not 90 degrees. They are three-dimensional. So the hydrogens are as far apart from each other as they can possibly be. So how do we go from Lewis to VSEPR shape? How do we go from a Lewis structure to the shape in VSEPR? Well, we draw the Lewis structure, and then we count the number of electron domains. Okay? Now, it says here the domains are only around the central atom. So when we're counting domains, we only worry about the domains around the central atom, not any other ones, because, as we'll see here in a little bit, something could have, for instance, on the one we just had before that had carbon and chlorine around them, each of the chlorines had a bunch of lone pair of electrons, okay? Each chlorine had 3 lone pair of electrons. However, those don't count because that wasn't the central atom. A single, double, or triple bond counts as one domain. We tend to call that a bonding domain, or a non-bonding domain, which is a lone pair. So even though double bond has 4 electrons being shared and triple bond have 6 electrons being shared, that is still only one domain. So we count the domains and the lone pairs, and then we use our chart to determine the bonding and non-bonding around the central atom and the shape. So if I look at this one right here, here is a water molecule. I can see that here's a bond, there's a bond. So those are single bonds. A single bond counts as a domain. So one domain, 2 bonding domains right here, and here's a lone pair of electrons or an unshared pair. Here's an unshared pair, a lone pair. So 2 non-bonding domains and 2 bonding domains. If you look at your chart, okay, if you look at your chart that you have on your AX packet there, what does it say for 2 lone pair of electrons and 2 bonding pair? What shape? Kara, what do you think? It's on the front. 2 bonding and 2 lone pair. Bent. Okay? Can everybody see that? That is bent. All right? Now look at this one. This is what I was talking about. See all of these unshared pair here of fluorine? Those don't matter. Those don't matter. Well, they do matter, but they don't matter when we're trying to find the shape because the central atom here is carbon. So how many bonding pairs does carbon have? 4. How many non-bonding pairs does it have? 0. So what is 0 lone pair and 4 bonding pair? What shape is that, Amelia? Tetrahedral. Good. Let's look at this one right here. Okay. Once again, all of these unshared pair are not around the central atom, so when we're determining the molecular geometry, we don't count those. So I have 1 bonding pair, 2 bonding pair, 3 bonding pair. Remember, a double or a triple bond only counts as 1. So I have 0 lone pair, and I have 3 bonding pair. So what does that tell me? 0 and 3. Tyler? Trigonal planar. All right. Now this one here, excuse me, this one here is diatomic, meaning there's only 2 atoms. So if I have this one, carbon has, when I have carbon, I always make carbon the central one, don't I? Okay. So carbon is my central atom. It has 1 bonding pair. Even though it's a triple bond, it counts as 1. 1 bonding pair and 1 unshared pair. So what's 1 and 1? That's not even on your list, is it? But you're going to see that this is going to be linear. It'll be on your AX list, okay, when we start doing the AX. Okay. Now, remember the big picture here, folks, okay? Electron domains are negative charges, so they are spreading out as far as possible due to their repulsion. Okay? Doing this allows the molecule to be most stable. Here's that chart I was just talking about when we were looking at that, and it has lone pair of electrons, bonding pair, and I believe I told you in the video to highlight these ones that were red, didn't I? Okay. So those are the most common ones that we will see, most common molecular geometries that we will see. So let's look at some examples here. Okay. VSEPR example number 1. We're going to go through a bunch of these examples, okay? Carbon dioxide, CO2. So what I need to do is I need to draw out my carbon dioxide. So I'm going to put carbon in the middle, and I know that carbon has 4 valence electrons. I'm going to put a single bond, or an oxygen onto that carbon, as so. Then I'm going to single bond another oxygen onto that carbon, as so. Each oxygen has 6 valence electrons. So I can see here that I'm not happy yet. Nothing is happy yet because I have not achieved the octet rule. Okay, I don't have a full octet. So what I'm going to do is I'm going to double bond both of them. So I have my double bond here. I have my double bond here. And now I obey the octet rule, correct? So when I do my dashes and draw this out, it's going to be carbon, oxygen, and I'm going to signify the lone pairs of oxygen. But when I look, I'm only determining the bonding, okay, the domains, I should say. I'm only determining the domains around the central atom. So I have 1, 2 domains. So I have 2 bonding. I have 0 non-bonding, correct? So what is 0 and 2 on your chart? What does 0 and 2 tell you, Carly? Linear. So when I look at this, 0 bonding, or excuse me, 0 non-bonding, 2 bonding gives me linear. Okay, wasn't too tough, was it? Probably the toughest part was drawing the electron dot, or the Lewis dot structure. Example number 2, BF3. Now, the thing about boron that you just need to memorize is that boron is an exception to the octet rule. When boron bonds, it has 6 valence electrons. So as I draw my boron, each boron has 3 valence electrons. So I'm going to bond 3 fluorines to it. As so. Now, once again, as I look at this, I count the domains, the bonding and the non-bonding. So how many bonding domains do I have, Carly H? 3 bonding domains. How many Paige non-bonding domains? Remember, we're only counting around the central atom. Okay. Huh? 0. Good. Were you counting all those ones around fluorine? Oh, maybe. Okay. I just kind of saw the gears turning in your head. So we have 0 non-bonding. We have 3 bonding. So, Madison, what does that tell us the shape is? 0 and 3. Trigonal planar. Okay, good. Trigonal planar. Yet another example. Here we go. NO2 -1. Now, we haven't talked about this. You'll get this today when you watch the video, because one of these things, it's called resonance diatomic elements and polyatomic ions. And here's the polyatomic T4D1 method that you're going to look at tonight on a video. But this is a polyatomic anion. Anion meaning it's a negative charge. Polyatomic, poly is many. Many atoms forming an anion. And that just means it's more than one. So when I look at this, I need to determine, first of all, my Lewis dot structure. So I'm going to say, okay, I don't have carbon, so I'm going to look at my electronegativities. Nitrogen is 3.04, oxygen is 3.44, so nitrogen has the lowest. So I'm going to have nitrogen be my central. And I know that nitrogen has 5 valence electrons. Now, what I'm going to do is I'm going to single bond 2 oxygens to this. So I always start out single bonding. So here's 1 oxygen. Here is my 2nd oxygen. Now, you notice nothing is obeying the octet rule here yet. Okay? So what I'm going to do is I'm going to take this one right here, this 1 electron that nitrogen has right there, and I'm going to make a double bond between this nitrogen. Didn't go quite how I wanted. I'm going to make a double bond between this nitrogen and this oxygen. So now, nitrogen's obeying the octet rule. That oxygen, I got 1 too many electrons there. That oxygen is now obeying the octet rule. But the bottom oxygen is still not happy, correct? Well, by having this negative charge, that means that I have an added electron. So that added electron, let's just say we put it right here. So now, is that oxygen happy? Yeah. And how I tend to do this is I put a bracket around that, and I say that whole thing is a -1, saying that it has 1 electron extra. Now, as I look at this, I still do the same thing. I count bonding and I count non-bonding. So, Stephen, how many bonding pairs do I have here? 2. Okay? Right here is 1. Right here is 2. Remember, the double bond still counts as 1. So I have 2 bonding pairs. How many non-bonding, Aiden? 1. So what is 1 non-bonding, 2 bonding? What is that, Cody? Bent, right? It is bent. Now, something to notice, okay? Something to notice. There are 2 bents on there, correct? What's the difference between the 2 bents? What is it, Kara? One has 1 lone pair and the other one has 2 lone pairs. Okay? So there's 2 different types of bent, just to be aware of that. Example number 4, CH4. We've dealt with this guy already. I'm going to draw him up here, though. I'm going to draw methane up here. So I have a carbon that has 4 valence electrons. Get that arrow out of the way. And to that, I am going to bond 4 hydrogens. So how many bonding pair, Tyler? 4. How many non-bonding pair, Amelia? 0. So what does 0 and 4 tell you, Carly? Tetrahedral. 0, 4 bonding, tetrahedral shape. NH3. This is what we commonly refer to as ammonia, not pneumonia. That's something in your lungs, getting fluid in your lungs, pneumonia. Ammonia is NH3. So once again, I know that I never put hydrogen as the central atom. So I'm going to build around nitrogen. Nitrogen has 5 valence electrons. So there's my 5 dots. I'm going to put a hydrogen here. I'm going to put a hydrogen here. I'm going to put a hydrogen here. So does everything obey the octet rule? Well, hydrogen doesn't, but once again, hydrogen does not have to obey the octet rule. Okay, hydrogen fills its outermost energy level with 2. So, Carly, how many non-bonding do I have there? How many? 1, right there, correct? 1 non-bonding. Paige, how many bonding? 3. So what's 3 and 1? Tell me. Madison, what does 3 and 1 tell me? Trigonal pyramidal, right? Trigonal pyramidal. Our 6th example is water. We've already done water, so I'm going to skip that one, but it is bent. 2 bonding, 2 non-bonding. It is the other bent, but we already said that one. So, lone pairs create a larger region of negative charge than bonding domains, okay? Simply put, for instance, let's take oxygen. Oxygen has 6 valence electrons. So when we had that water, it had 2 non-bonding and 2 bonding. Those non-bonding electrons, those lone pair of electrons, are only with the oxygen, right? They're not being shared. So those create a larger negative charge. So lone pair of electrons push further than what a shared pair of electrons pushes. Okay? So that gives us the differences in the angles. How many lone or unshared pair that we have. If you look at this, okay, tetrahedral we said was 109.5 degrees because tetrahedral has 4 shared pair of electrons. Now let's look at this one. This one has 1 lone pair right there. So this ammonia has 1 lone pair. So that lone pair pushes at all 3 of those paired shared pair of electrons. So they're going to push, that lone pair is going to push a little bit more. So the bond angle is going to be decreased a little bit. So that 1 lone pair gives us a 107-degree bonding angle. And here is oxygen. Notice that oxygen has not 1, but it has 2 lone pair of electrons. So that's going to push this bonding pair here and this bonding pair here closer and closer together. And that bonding angle comes to be about 104.5 degrees. So the number of lone pair depends on or pushes the unshared, the shared pair together. Now, we have something that we refer to as AXE notation, A-X-E. It's just a shorthand version of writing down what we were just doing there, counting our domains. So if you look at your AXE packet, this is going on the back part of it. So I look and I say, okay, here is ammonia. Once again, I know that ammonia has 1 lone pair and it has 3 shared pair. So when I go AXE, A is the central atom, X is the bonding pairs, and E is the lone pair of electrons. So as I look at this, AX3E1, and you have in your packet AX3E1, don't you? What does it say it is? Trigonal pyramidal, right? Now what I want you to do, is I want you to look, okay? I want you to look back in the second and third page here where it describes the AX method, okay? Find trigonal pyramid, okay? Find trigonal pyramid. And you should see something that looks like this. Right? See where I'm at? Did you find it in your packet? Okay. Now, that is the AX method. So when I am drawing this out, I'm going to replace the A. I'm going to replace the A with what's in the middle, with N. Okay. I'm going to replace all the X's. I'm going to replace all the X's with hydrogens. And I'm going to replace the E with that lone unshared pair. So if I am writing, this is what we call, this right here is what we call a Fisher projection. Okay? That is the Fisher projection. So that's how I would draw ammonia. Okay? Now I'm going to look here at water again. So water, when I go AXE, I have AX2E2. AX2E2, and this tells me, okay, that I have two bonding pair and I have two lone pair. So AX2E2 tells me that I have a bent shape. Now remember, I told you that there were two different bent shapes. So I'm now going to go back and I'm going to find the AX, okay? I'm going to find the AX for the bent that has two unshared pair. So when I do that, I'm going to see that it says A, X, X, E, E. See where I'm at? Now, all I need to do, once again, is substitute in. I know that my A and my X, A is oxygen, and the X is hydrogen. And then my lone pairs are my E. So there's my lone pair of electrons. So there is my Fisher projection of water. Here is methane. Yeah, here is methane, CH4. So when I ax that, I have, okay, AX4E0, which tells me that that is tetrahedral. Okay, it's tetrahedral. So I go through it and I find my tetrahedral, and my tetrahedral looks as so. A, X, 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 SO. So once again, all I need to do is fill in my A's and my X's, and I know A in this case is C, and all my X's, bad H, whoa, all my X's are H's, as so. So I just draw out my different ones using dashes, using a wedge or a triangle, and then using dashes. Okay? Now, what do those mean? That's the big thing. What do those mean? Well, our Lewis structures are two-dimensional because they're on a piece of paper. So how do I signify that there's a three-dimensional shape? I use, okay, so I'm looking at this and I say, okay, here's the shape of that. Here's the shape of ammonia here. Here's the shape of water here. So how do I signify those when I'm only using two-dimensional series? Well, look up here. I have the dashes, I have the wedge, and I have the lines. So on my Fisher projection, what they actually mean, okay? A bond is on the plane of the paper. A wedge or a triangle is projecting in front of that plane, and the stacked lines are projecting behind that plane. So when I go all the way back, okay, and look at this, I say, okay, let's look at methane here. This and this is a dash, so that is on the plane. This H is going behind or into the wall, so to speak, and this H is coming out at us. Okay? Remember that these are not two-dimensional shapes. So if I would have a molecule, and I have a model kit that I built this with, okay, you can see that if I have these two being on the plane right here, okay, there's my plane, and you can see that one goes in front of the plane, one goes behind the plane, right? So that's what this wedge and that dash signifies. Okay? Do you think, give me a thumbs up, do you think you can tell me what geometry each molecule is by counting the domains, the bonded domains and the unbonded or non-bonded domains? We okay with that? All right, good, good.